Okay, students, so we'll go to the last topic of module number 1, that is encoding of machine instruction. Okay, so now we will be discussing not in deep exactly, because this is a concept of compiler design exactly, like how these instruction should be converted into a opcode or else in a binary pattern. Clear? Okay, parser we need, okay, lexical analyzer we need, okay, many more concepts we need to discuss, so that we will be discussing under system software and compiler design topic, okay, from semester number 6 exactly. Okay, but for time being, we'll see like on what manner the instruction will be converted into a binary pattern. Okay, so where we will be having just a glance or a basic information like how it will be done. Yeah. Okay, so just observe. So here we got the assembly language instruction. Consider like add R1 comma R2. Okay, we need to perform an addition operation between register number 1 and register number 2. Okay, so that is what the instruction if you are having, consider it. So this should be provided as an input for the assembler program. Okay, now what exactly this assembler program means? Okay, so he is responsible for converting assembly language instruction into a binary pattern. Remember, okay, so inside this itself we are using lexical analyzer, parser, parse tree, okay, and many more things. Okay, so the compilation part is fine. So using those logic or using those programs, inbuilt systems of the program, what assembler will do is he will just convert the assembly level language instruction into binary pattern. Remember this. Okay, fine. So on what manner it will be converted or it will be compared, okay, we'll see this now. Okay, the type of operation that is to be performed and the type of operation used, okay, may be specified using an encoded binary pattern referred to as opcode, okay, for a given instruction. Okay, so in our example I am taking it as add R1 comma R2, right? So that add instruction should be represented in some other format, so that your system should be able to understand that yes, we need to perform a addition operation between R1 and R2. Okay, for that this assembly level program or assembler program will generate a code that will be called as opcode. Okay, by identifying by reading that particular opcode, your system will be able to understand that yes, I need to perform the addition. Clear? Okay, fine. So next, for representing this opcode, okay, observe it, for representing this opcode, okay, how many bits we need, we'll see this. Okay, suppose 8 bits are used to represent the operation specified in assembly language instruction, that is nothing but the opcode. Okay, then we can have 256 different possible instructions. Okay, see, if we are expecting total 8 bits, okay, to represent this particular opcode, see how many bits we are having, 32 bits we are having. Okay, in our examples and all, we are considering the instruction of what, 32 bit exactly. Out of this 32 bit, if we are consuming 8 bit to mention the opcode, then how many different instructions I can represent? 256. Okay, 0 to 255. Okay, 0 to 255, that is what the maximum capacity of accommodating numbers using 8 bit. Remember, starting from 0 to 255. If I want to represent these number between 0 to 255, I need minimum 8 bit. Remember, in case of binary, if I want to represent it. Clear? So 8 bit will be allotted for this particular opcode. Okay, opcode is representing what? Add instruction. Remember. Okay, now the question is how I can represent R1 comma R2, right? Yes, I'm done with representing add instruction with opcode. Okay, then how about R1 and R2? We'll see this. The rest of the 24 bits are used to specify the rest of the required information. Okay, so out of 32, we consumed already 8. So what is left? 24 bits are used to specify the rest of the required information. Okay, we'll see this. What are those required information? Obviously, it is source and destination. But remember, not only the source and destination, there we are using addressing mode. Remember this, right? For mentioning the source and destination, okay, to find the values which is residing inside the source and destination, what we do, we are using 8 different addressing modes, okay, which will help our system to trace the required input. Clear? So now Along with representing those source and destination address, we need to use this 24-bit. Remaining, we have only 24. We need to use this 24-bit so that we can accommodate all those addressing modes also. Clear? Okay, fine. We'll see this. How many bits we are left with? 24 bit. Okay. So add R1, R2 was like easy example what I took. Okay. So for the representing add instruction, 8 bit I need for generating the opcode. Okay, let it be. Then general purpose registers we are having, right? N general purpose register. We are calling it as 4 bits. Okay. The address of this like address of R1. Okay. So we are considering like total 4 bits we need if I want to represent the address of the general purpose register 0 to n. Okay. So using 4-bit, how many like values we can accommodate? 15, right? 16, right? Okay. 0 to 15, right? 4. Like continuous 4-bit. Okay. If you are having 4 ones, 8 plus 4 plus 2 plus 1. 8 plus 4 plus 2 plus 1. How much it will be? 8 plus 4, 12. 12 plus 2, 14. 14 plus 1, 15 exactly. Okay. Like, yes. 18 plus 4 plus 1. Okay. Like 12, 14, 15. Exactly. 0 to 15. Okay. Means total 16. Okay. Total 16 bits we can accommodate using 4-bit number over here. Okay. So here n will be maximum 16. That's it. Okay. So now consider like we are having general purpose register like 0 to 15. Okay. So to represent the number of that particular register, we need 4 bits over here. Okay. So in your instruction, if you are using source as well as the destination, both registers, then 4-bit is enough. 8-bit we already consumed, 4-bit for source and 4-bit for destination. Total how many bits? 16 bit. What is the remaining bit? The remaining we have only 16, right? So now we'll see. Okay, using the 16-bit, how we can accommodate rest of the like addressing modes or rest of the instructions and all. Okay, so now in this example, just observe source and destination both are having the registers. Okay, fine. But here what we are using index addressing mode. Remember this, we are using index addressing mode. We are having the offset 24. It represents what? Index addressing mode. Means the value of R0 should be considered as an address. For that address, I need to add, so for that address, I need to add 24. So whatever the effective address will be generated, so that should be moved to R5. So this is what the meaning of move 24 within a bracket R0, R5. Okay. So if I want to represent this using the encoded version of a machine instruction, then 8-bit I need for opcode, that is for move. Okay. 4-bit for source, address of R0, 4-bit I need, 4-bit for destination, right? Okay. So total how much? 16 exactly. I'm left with 24. Wait for it. Okay. See here, 3-bit we need to specify an addressing mode. Remember, why I need 3-bit to specify the addressing mode? How many addressing mode we have? Only 8, right? Only 8 we are having. If you start naming all those addressing mode from 0, okay, so how many bits we need? Okay, only 8 bits we need. Okay, with using 8 bits, I can accommodate all the 8 numbers starting from 0. 0, 1, 2, 3, 4, 5, 6, 7. How much it will be? Total 8. Okay, so using 3-bit, I can easily accommodate value 8 exactly, right? That's why we are utilizing 3-bit to represent addressing mode. Okay, so here how much? Like here we need 3-bit. Here also we need 3-bit. Remember, and plus 3-bit were needed to specify where should addressing mode affect, either source or destination. Okay, which addressing mode is utilized? For that we need 3 bits. Okay, where it is affecting, either source or destination, for that we need 3-bit exactly. Okay, so now see here totally how much it was without any addressing mode. Here without any addressing mode, 16 we were expecting, right? Okay, 8 for opcode, 4 for resource, 4 for destination, total 16. Now 3 plus 3 got added over here, right? So 16 from here plus 3 to specify the addressing mode, plus 3 where exactly it is affecting, whether it is in a source location or whether it is in a destination location. How much it will be? 22 bits. Remaining 10 bits to specify offset 24. Okay, so rest of the 10-bit whatever we are having, see 22, capacity is 32. Okay, left is what? 10-bit exactly. 10-bit will be utilized for other information or else for this kind of offset. This is what we are representing over here. Opcode 8 bits, source 7-bit, destination 7-bit. Don't get confused. This was in a representation like 8 plus 4 plus 4. Okay, But here we are adding 3 over here. Why? Because of this. Okay, so here we are adding 3, here we are adding 3. Okay, don't get confused. Both are same. 8 plus 7 plus 7 plus 10 exactly. 7 plus 7, 14. 14 plus 8, 22. 22 plus 10, 32 exactly. Okay, total 32 bit will be utilized in this fashion. But we have a problem. See, in this instruction, only registers we are involving. If we are involving any memory location like LOC or else some, okay, such kind of location, then how it will be? We'll see this. If you want to specify a memory operation using the absolute addressing mode, example here, move R2, R location. This is the absolute address of a location exactly, right? Okay, this is what a fashion of what absolute addressing mode. If this is what the case, then how it should be dealt? Okay, so now as usual, 8-bit we need for opcode. Then for mentioning the address of R2, we need 4-bit, right? Then to mention the addressing mode, we need 3-bit. To mention the addressing mode, where exactly, whether it is in the source or destination, to represent that, we need 3-bit. How many bits it is? Total 18-bit. Here, 8 plus 4 plus 3 plus 3. 3, 3, 6, 6 plus 4, 10, 10 plus 8, 18 exactly. What you are left with? Here, remaining 14 bits are not enough to accommodate address location LOC. The only solution is include a second word as a part of this instruction. Okay, means here 32-bit will be utilized over here, right? Okay, apart from that 32-bit, another 32-bit will be utilized. Okay, if that is the case, we are calling it as 2-word instruction. Why we are doing so? Because location, okay, address, whatever we are having, original address, this is what a label exactly. Okay, original address of this, if I want to represent it by other information, okay, what I left with is only 14-bit. This is not enough to accommodate LOC. So what we need to do, we'll leave this 14-bit as it is. Okay, it will be utilized for any other purpose. Okay, we are acquiring this second word. If it is the first word, second word will be acquired to maintain the address of this particular location. If this is the case, we call it as 2-word instruction. Okay, we call it as 2-word instruction. See, for your understanding sake, I'm providing this space. It should be a rectangle separated by 4. Okay, 4 boxes it should be. Okay, like 1 row, 4 column it should be. Okay, so in your textbook, you have a better representation of this. For the pictorial representation itself, I'm designing like this. Yeah, okay. So next, so this is what the last topic, the complex instruction step computer. Okay, that we are calling it as CISC, complex instruction set computer. See, in the previous whatever like 2 address instruction we have got, right? So 2-word instruction. So this we are calling it a complex version. Complex version. Okay, that's why complex instruction set computer CISC has been used to refer to processor that use instruction set of this type. Okay, like 2-word instruction if you are using, then that computer we are calling it as what? Complex instruction set computer exactly. Okay, but if you are imposing some restriction like it must use only 1 word, then we are calling it as RISC. Okay, RISC stand for the restriction. Okay, that an instruction must occupy only 1 word has led to a style of a computer that have been known as that have become known as, okay, reduced instruction set computer, or else RISC we call it as CISC and RISC. In case of CISC, multiple, like more than 1 word will be utilized for accommodating the complete instruction, but in case of RISC, only 1 word will be utilized for accommodating the instruction. If that is the case, the computer will be called as a RISC. If 2 word if you are acquiring, then it will be called as a computer of type CISC exactly. Okay, both are available, don't worry. Okay, so now like one common approach, okay, what we can do to overcome these kind of CISC kind of approach is what? The RISC approach introduce other restrictions such as that all manipulation of data must be done on operands, okay, that are already residing inside the processor register, okay, or else if you want to make any operation, okay, over a data, first what we need to do, we need to bring them inside, observe it, we need to bring them inside the processor register, and later we need to perform the operation. Then these kind of like location and all whatever we had, right? Okay, such kind of operation or such kind of problem we may not face. Okay, see, before this, if you are moving the content of location to any one general purpose register, then obviously we can accommodate using single word, right? Okay, but here due to this location, okay, due to the shortage of memory bit for accommodation, what we do, we are acquiring the second word. Okay, so that should not happen. If you want, okay, then we can accommodate all the values which should be manipulated, okay, into being in processor register, and we can perform the operation. Okay, so here three operand instruction we are representing. Okay, opcode 8-bit, RI 4-bit, RJ 4-bit, RK 4-bit. Okay, total how much? 4, 4, 4, 12. 12 plus 8 exactly, 20. So what I left with? I left with 12 exactly. I left with 12 exactly. So plus 3, plus 3, plus 3. Okay, it is also possible. Or as those 12, I can accommodate, I can provide it for other information. Okay, so this is what three operand instruction. Okay, see here, in case of this, fine, this will be like, let me take one example, like move, okay, move R1, comma R2, comma R3. Okay, so these two will be the source, and this is what the destination, right? Okay, to represent where it is affecting the addressing mode and all, we need 3 over here. For representing the destination, we need 3 over here. Total 6 exactly. 6 for representing the addressing mode. Okay, 12 for representing 12 for representing this particular address of the register, plus 8 bit we need to represent the opcode. So 8 plus 12, 20, 20 plus 6, 26 exactly. So 26 we have. Okay, what is the rest of the value? Okay, so my like minus 32 means, okay, we will be getting how much exactly? 6 plus, like 4 plus 2, we are getting 6 exactly. So 6 bit will be available in the other information section. Okay, means using this 32 bits itself, we can accommodate like 3 different operands. Okay, if you are dependent on registers. Okay, okay, students. So this is what the complete module number 1. Okay, very, very important. You may feel bit huge module, okay, because concepts are more, but very basic concepts they are. Okay, it is easy to understand, and we can expect some important questions also. Okay, so I will just give the assignment questions. Fine. Try to submit soon. Okay. Okay, students. Thank you. So we'll meet with the module number 2 in next video. Thank you, students.